I would like to go over the derivation for the formula of the surface area of a cone. So here I have a net of a cone, which is comprised of a circle as well as a sector, a circular sector. I'll call the surface area of the cone base, okay? This is the circle base of the cone. I'll call its area SA1, and then the circular sector, I'll call its area SA2. Now, the circle has a radius of r, and for the sector, it has an arc length over here. But because when you fold this sector up and curve it, this arc length has to enclose this length over here, the circumference of the circle base. So it means that these two are the same. So this circumference is going to be 2 pi r, right? So then this arc length is also going to be 2 pi r. This part is going to be the slant height, which is going to be s, the slant height of the cone. And here we have an angle, theta, okay, which will be used later on. Now, the surface area of a cone, this is going to equal to SA1 plus SA2. We know how to find SA1. That's pretty easy. It's just the area of a circle, which is going to be pi r squared. Now, SA2, which is the area of this sector, that's a bit harder to find, but we can use some common ratios to help us. So if we consider this sector over here, we have an angle theta. And if we were to take the angle theta of an entire circle, which is going to be 2 pi radians, that corresponds with the area of the entire circle. Okay, so if we somehow imagine that we have the entire circle where s is the radius of this larger circle, okay, then 2 pi radians would correspond to the area of the entire large circle, which is going to be pi s squared, okay, because s is now the radius. Now that is equal to this angle in theta corresponding to the area of the sector, which is going to be SA2. Now, the problem we have here is that we have two unknown variables, theta and SA2. SA2 is what we want to find. Is there a way for us to isolate for theta or write it in terms of other constants that we know, such as s and r? Well, let's see. We're going to use common ratios again. So instead of looking at area, let us look at arc length. So the angle of an entire circle in radians is 2 pi radians, and that would correspond to the arc length of an entire circle, which is the circumference of the entire circle, which is going to be 2 pi s, okay? Because s is, again, the radius of the larger circle. So 2 pi to 2 pi s, and that is going to equal to the ratio between this angle theta in radians to its arc length, which is 2 pi r. Isolating for theta, we get theta is equal to 2 pi r over s. And this is neat because we can plug this into here, and then we're going to get 2 pi r over SA2 times s. Isolating for SA2 between these two expressions over here. So with this equation, we isolate for SA2, and we get that SA2 is equal to pi rs. And that's really neat, because now we know what SA2 is, pi rs, so we can say that the surface area of a cone, which is SA1 plus SA2, is equal to pi r squared plus pi rs. Now this was an interesting way to find what SA2 is, okay, using some ratios, okay, as well as geometry. But let us now use calculus to find out what SA2 is. When it comes to calculus, we are going to be using the surface of revolution technique to find out what SA2 is. So here we have a diagram, okay? On the Cartesian plane, we have the x-axis, we have the y-axis, and I'm just going to have a cone right over here. Let's say the cone is tipped over, and it looks something like this, okay? But how do we get this shape? Okay, now this is just SA2, okay? So you can pretend that the inside over here is hollow. Now, in order for me to get to this shape, I actually have to do a revolution. So here we have this line segment, or you can say a line, right? Y equals to mx, it's linear, but I'm only going from 0 to h, and h is actually the height of the cone. Okay, so this is the height of the cone. So y equals to mx. And then I will do a surface of revolution, we will take this line segment whose corresponding x values go from 0 to h, all right? And then we're going to spin it around. If we revolve it around the x-axis, we will get the outer surface area for the cone, okay? Now we do know that this right over here is actually the radius of the cone base, okay, this length over here, okay? And then that radius is going to be m times h, because when x is h, I plug it into here, and then I get y equals to mh. But this y, okay, this y corresponds to the actual radius of the circle base. So r equals to mh, and we want to isolate for m, which is equal to r over h. This will come in handy later. So with the surface of revolution formula, we have 2 pi integral from 0 to h of f of x dl, where dl is my differential for the arc length. And f of x is y, which is mx, and dl is actually the square root 1 plus dy dx whole thing squared dx. Okay, so this is your derivative. Okay? And we know what the derivative is because our function output is y equals mx, and its derivative, it's just m. So we have m for dy over dx, and you square it, so you get 1 plus m squared dx. This is nice because m square root 1 plus m squared is a constant with respect to x, so we can pull it out of the integral. And we have the integral from 0 to h x dx. Integrating that, we get x squared over 2. We're going from 0 to h. Plugging in h into x, I get h squared over 2, minus plugging in 0 into x, I get 0. So that just leaves me with h squared divided by 2. The 2's will cancel out, so I just get pi m root 1 plus m squared h squared. Now you see right here that I have this m, and I don't really want that. I want to write it in terms of stuff I know, for example, the radius and the height. Okay, which is going to be pi r over h square root 1 plus r over h squared, once I substitute r over h into m. And now this h and one of these h's will cancel out, so I get pi r h root 1 plus r over h squared. And if I take this h and I bring it inside the square root, I have to square the h if I bring it inside. So I have h squared times 1, which is h squared, and then h squared r squared over h squared. Those h squares will cancel out, so I'm left with r squared. But sometimes we don't know what the height of the cone is, okay? Let's say we want to write it in terms of its slant height, but that's okay, because if we take a look at the cross-section of the cone when it's tipped over like this, okay, it's gonna be a right triangle over here, okay? And we see here that we have h, we have r, and we have s. So we have a nice right triangle. Using the Pythagorean theorem, we have s is equal to the square root of h squared plus r squared. So this means that I can substitute this with just s. And there we go. We have pi rs again. This uses another method to find SA2, but ultimately SA2 is going to be pi rs. So this is how you derive the formula for the surface area of a cone.